The periodic table is kind of a big deal, and it's very intricate. There's a lot of different things that the periodic table can tell us. There are patterns throughout the periodic table. Right, there are patterns, and we call those trends. And the trends have things like mass, size, like radius, reactivity. There's a lot of other trends that we see on the periodic table. So by knowing the position of an element on the periodic table, you're able to figure out exactly the reactivity and everything with it. There are two things that will affect periodic trends. The size of the atom. The size of the atom is a major one. And also how strongly, or how many valence electrons it has. I'm sorry, the size and the number of valence electrons. And we'll talk about those. First one, mass. Mass is the easiest periodic trend in the entire world because the mass is written on the periodic table. As you go down the periodic table, it should not shock you that the mass goes up. Why does the mass of an atom increase as I go down the periodic table? As I go down a column? What am I adding? Why is potassium heavier than sodium? Yeah, why is the mass higher? Yes, thank you. I'm adding protons and neutrons, all right? As I go down the periodic table, I add protons and neutrons. So the higher the atomic number, generally the higher the mass, because I'm adding more protons and neutrons. All right? I will never ask you on a quiz for the mass trend, because it's written on the periodic table. If you can't look at two numbers and see which one's bigger, then you've got other issues and you won't do well on the test anyway. All right? Next one. Radius. Atomic radius. As I go down a group. Hey, Sultan, you should probably take these notes instead of Snapchatting? Was that I didn't know if that was a Snapchat. Oh, okay. All right. Atomic radius. As I go down a group, my atom gets bigger. So as I go down the periodic table, the atom gets bigger. Size-wise, radius-wise, right? You guys are learning in geometry that radius is from the center of a circle to the perimeter of it. Okay, but at some point you learned that. At some point you know what radius is. As I go across a period, the radius increases. All right? Or I'm sorry, the radius decreases. As I go across a period, the radius decreases. All right, so let's think about this for a second. Let's say I have lithium. What's the atomic number of lithium? 3. 3. All right, so how many protons does lithium have? 3. All right, and we'll pretend that this is the radius of lithium. We'll pretend that that circles the electrons. How many energy levels does lithium have? Does anyone know? No. How many energy levels? 2. How do you know it's 2, Jalen? Yeah, it's in the second row, right? 2 energy levels. The row is the energy level. It's in the second row. Francium is element 87, so it has 87 protons, right? And it has 7 energy levels, right? That means that it's going to be bigger because it has more energy levels. So the radius is just generally bigger because I have more levels of electrons, okay? The radius is from the center of the nucleus to the farthest electron. Does everyone understand why as I go down it gets bigger? Because I add energy levels. However, let's say I've got lithium. Here's the weird thing. As I go across the row, it actually gets smaller. As I go across my row, it actually gets smaller. Does anyone know why? Does anyone know why as I go across a row, it actually gets smaller? The radius of the atom. As I go across from lithium to fluorine, my atom gets smaller. Does anyone know why?
Because you move down in the columns now?
No, I'm not going down in columns. I'm going across a row. All right, what's the atomic number of fluorine? 9. So it has 9 protons, right? So we can think of lithium as having 3, a nuclear charge of 3. The nucleus has like a plus 3 because it has 3 protons. Fluorine has 9, right? With me? So that means, let's think of an atom like a magnet. All right, lithium only has a plus 3. So it doesn't pull on those electrons very strongly. Fluorine, on the other hand, has a 9 charge. So it's able to pull on those electrons much tighter, and it pulls those electrons inward. Think about, like, let's say, if I were lithium and Grabaric were fluorine, okay? Grabaric's stronger than I am. I'm confident enough in my fitness level to admit that. Grabaric, you might not have realized, Grabaric's stronger than I am. So if me and Grabaric were pulling on something, he'd be able to pull it tighter. He'd be able to pull it closer, right? Because he's stronger. Fluorine can pull things in tighter because they have a stronger charge. I'm lithium, he's fluorine. I can still hold on to something, but he's able to pull it in much tighter because he is so much stronger. All right? So it's the nuclear charge. That's what causes it to be pulled in. And that's going to be really super duper important. Okay, reactivity of metals. As I go down the periodic table, it turns out that the metals become more reactive. So as I go down my periodic table, my metals become more reactive. And as I go across, they become less reactive. What element do you think is the most reactive metal? What element? Can you guys guess what element is the most reactive metal?
81H. 108.
H is not, although you're in the correct column, which is FR, francium. As I go down my periodic table, they become much more reactive. All right? And that all has to do with the radius. Think about it. FR has a super big radius. Right? FR, whoops, I'm in the wrong tool here. FR is going to have a really big radius because it's got 7 energy levels. So those electrons are going to be way out there, right? No, they're really, as I go to the right, they're really close. So FR is really big, all right? I'm FR, all right? I've got those electrons way out there because I'm pretty weak. A metal reacts by having something take its electron. So when a metal reacts, its electron's being stolen. So if I'm really weak, and I have a real weak grasp on an electron, Grabaric can come by and steal it, right? Because he's really strong. So if I'm really weak and my electrons are way out there, it's really easy for an element to come by and steal the electrons. And that means my metal will react. Right? So FR is the most reactive because the electrons are hanging way out, far away from my nucleus. Okay? Non-metals are the exact opposite. Whoops, sorry. Non-metals are the exact opposite. Non-metals react by taking electrons, by stealing the electrons. Metals kind of give them away. Non-metals steal them. So a non-metal steals the electrons. So you want really tiny nuclei. You want those strong Grabarics and Powers to come by and steal those electrons. All right? Maybe even a Schultz. I don't know. I think he's wirely.
Did you say he's widely?
Wiry. I don't, he doesn't look super strong, but I bet he is. Schultz? No, not computer Mr. Schultz, like gym teacher Mr. Schultz. Like wrestling coach Schultz. Computer Schultz, I don't think is as strong as gym teacher Schultz.
Is he stronger than you?
Computer Schultz? Yeah. You know, believe it or not, we don't have strength competitions after school. I just assume like Grabaric and Powers are stronger than me.
How about you? They should do a fundraiser.
I don't think I could take
it. Mr. Bender was like the coolest teacher in school.
What?
Yes, I can do me. So, non-metals steal the electrons. So we want very small radii on my non-metals. All right, ionization energy. Ionization energy is the energy required to lose an electron. All right, so it's how easily an electron falls off an atom or is taken, or how easy it is to steal an electron. Steal an electron?
No. He was walking out and she was walking in at the same
That's magic. Okay, so think about it this way. If I'm francium and Grabaric is fluorine, Which one do you think is going to be easier to take an electron from, me or Gerberic? Me, yeah, right? So francium has a lower ionization energy. It's easier to take it from me. Whereas Gerberic, like, let's say you have a protein drink, trying to wrestle a protein drink away from Gerberic is impossible. Right? He'll revert to biting before he gives up his protein shakes. Okay? So ionization energy is the energy needed to lose an electron. If I add energy to an atom, I can strip electrons off. So it's how much energy is required to strip that electron. Metals have low ones because they're big and they give up their electrons. Nonmetals are tighter and they take electrons. Okay, next up, electronegativity. It's how much an atom wants an electron. It's the attractive force for an electron. It's the same deal where if I am a small atom, small atoms attract electrons more because they can get closer to the nucleus. Right? Think of that protein drink example. Who do you think wants a protein drink more or a protein shake? Me or Gerberic? Gerberic, right? I mean, come on. So fluorine, Gerberic, fluorine number 9, wants that protein shake more than I do. He is more electronegative. All right? He's more electronegative. I don't care about it. I'll toss it to him.
I'm taking the TCG over there.
It's kind of intimidating. He's very intense. I think all wrestling coaches have to be pretty intense, though. Like who? Like Schultz is pretty intense. Powers is intense. Raven good? I don't get the same feeling. I feel like he's more laid back. All right. Electron affinity. These are all very, very similar. I can when we're done. Electron affinity. That is the energy change when a neutral atom gains an electron. So it's how much energy, the change in energy when an atom gains the electron. It's very, very similar to like electronegativity and things like that. And we'll go over these in a second and you'll see. But I'm not a big, huge fan of electron affinity. I don't think it really...
Why not?
I think the other ones measure it just as well. Why memorize a third thing if you've got two that already deal with it? You know, it is what it is. All right? Yeah. Yeah. All right. Okay, so we're going to kind of talk about these a little bit more, but these are the general trends. These are the main trends. There's a lot of trends. These are the ones that you're going to have to know and you're going to have to kind of remember because these are the ones that talk about reactivity and the movement of electrons. Okay.